So, good morning to all. Today we are going to discuss about the topic MO theory. So, myself is Dr.C.Thangapriya, Assistant Professor of Chemistry in SFR College for Women, Sivagasi. So, let's go to the topic MO theory. MO theory means molecular orbital theory. MO theory is the basic for explaining the various properties of the molecules such as the magnetic properties. There are various theories explain these properties, but when the MO theory clearly pictorially represents how the magnetic properties varies for the molecules. So, let us see the theory. So, objective is what is the need for the MO theory, postulates of MO theory, MO diagram for homonuclear diatomic molecule and the MO diagram for heteronuclear diatomic molecule. These are all discussed in this video. Let us see. First of all, postulates are features of MO theory. So, what is the need for MO theory is already the Lewis VB theory, valence bond theory explained the proper structure of the molecules, but they won't explain the various properties such as magnetic properties. The MO theory explained the magnetic property. For example, we know that oxygen molecule O2 is a diamagnetic character, but based on the VB theory and Lewis theory, but in the MO theory explained that when the oxygen molecule in the liquid form, it shows the paramagnetic character. This is not explained by the VB theory and the Lewis octet structure. So, the MO theory is needed to explain these properties. So, in order to go through the MO theory, first of all you know that atomic orbitals. All the atoms consist of electrons. These electrons are located in the atomic orbital. These atomic orbital are present around the nucleus in the series form as 1s, 2s, 2s1, so 2s, 2p. These electrons are filled according to the Afoff principle, Pauli's exclusion principles and Hooke's rule. In the MO theory, it proposed that when two atomic orbital is combined, it forms the molecular orbital. That is the first theory, first postulates. When two atomic orbital is combined, it form the molecular orbital, two molecular orbital. That is the number of atomic orbital combined, it gives the number of molecular orbitals. Of these formed molecular orbital, half of the molecular orbital, that is for example, when two atomic orbital is combined, it form the two molecular orbital. Out of the two molecular orbital, one is the bonding molecular orbital and another one is the anti-bonding molecular orbital. In the next diagram is 1s atomic orbital in the left side and the another 1s atomic orbital in the in the right side. These two atomic orbital is combined to form this molecular orbital which is presented in the center of the diagram. That one molecular orbital is bonding molecular orbital and another one is the anti-bonding molecular orbital. We know that the molecular orbital is always present in lower energy than the atomic orbitals. That is, bonding molecular orbital is always present below the atomic orbital, whereas the anti-bonding molecular orbital is present above the atomic orbital, which is shown in the diagram. The bonding molecular orbital having lower energy and is represented as sigma, pi, del, whereas similarly the anti-bonding molecular orbital is represented as sigma star, pi star, del star, which is in the higher energy. So, next one, how the MO theory explain how the two atomic orbital is combined. So, before we discuss that, in MO theory also explain one of the term bond order. The bond order means it explains the number of bond present between the two atoms, that is the number of covalent bond is present between the two atoms. So, for example, suppose the bond order is 2, it means that the two atom having in between the two atom there is a one bond order is 2, between the two atom there is a number of bond present between these two atom is 2. Suppose if the bond order is 0, it means that based on MO theory, it means that there is no molecules exist in the world based on MO theory. These are the concepts explained through the bond order. The formula for the bond order is NB minus NA by 2. Well, that is Nb means number of electron present in the bonding molecular orbital, whereas the Na is the number of electron present in the anti-bonding molecular orbital. So when we subtract these two bonding as well as anti-bonding electrons and divided by 2, we get the bond order. So, how the atomic orbital is combined to form the molecular orbital? This is explained through the LCAO theory, that is the approximation method. It is said that when the two atomic orbital linearly combined, it form the two molecular orbital. One is bonding molecular orbital and another one is anti-bonding molecular orbital. The bonding molecular orbital is in the lower energy as well as the anti-bonding molecular orbital higher energy. Why these two bonding molecular these two molecular orbital having different energy? They combined through two atomic orbital of equal energy, but we get the bonding molecular and anti-bonding molecular orbital of unequal energy level. So how this is formed? So this concept is explained through the approximation method. In the approximation method, it represents that when two atomic orbital is combined to linearly to form two molecular orbital. So during the combination, the two atomic orbital is combined to form a wave function or in phase level. That is, in phase level means it is shown in this diagram. In phase means all the energy level are in the same and all the energy level are in the same, whereas in the out phase one is in the upper node and another one is in the lower. So during this upper and lower level, that is the out phase combination, a node is present. A node means and that at that place there is a no electron density is found. We call that place as a node. So during the formation of the anti-bonding molecular orbital, a node is formed, but it is not possible in the bonding molecular orbital. So due to this variation, it shows the energy variation, that is the bonding molecular orbital having a lower energy than the atomic orbital, whereas the anti-bonding molecular orbital having a higher energy than the atomic orbital. This is pictorially represented in this diagram. One as atomic orbital and the another one as atomic orbital is present in the left and the right side of the slide, whereas in the center the molecular orbital is formed. The bonding molecular orbital is represented in the lower energy level, whereas the anti-bonding molecular orbital is represented in the higher energy level. We already said that there is a node is present in the anti-bonding molecular orbital. So yeah, the two energy in the two node between the two shapes there is a one space is present. We call that as a node. This is the anti-bonding molecular orbital. Now we discuss how the MO diagram is formed for the homonuclear diatomic molecule, that is a hydrogen molecule. We already know that hydrogen is the first member in the periodic table. Each hydrogen, so in H2 molecule there is a 2 hydrogen is present. So each hydrogen having atomic number of 1, that is hydrogen having atomic number 1. So their electronic configuration is 1s1. So when two atoms, that is one atom is present in the left side and another atom is present in the right side, in the center there is a bonding molecular orbitals. In the left side 1s atomic orbital is present having one unpaired electron, it is shown in the left side, whereas in the right side another 1s atomic orbital of another hydrogen atom is represented in this. They are both in the same energy level. When these two 1s atomic orbital is combined, it forms the two molecular orbitals, that is one is bonding molecular orbital and another one is anti-bonding molecular orbital. It is represented in the lower energy level bonding and higher energy level is the anti-bonding. So hydrogen having one unpaired electron, similarly another one hydrogen having a one unpaired electron. When these two unpaired electron is combined to form a molecular orbital, this two electron is present only in the bonding molecular orbital. So it is in this bonding molecular orbital, similar to, we already said that based on the Afa principle, Pauli's exclusion principle, these two unpaired electrons must be present only in the bonding molecular orbital. Only 2 electron is available for the hydrogen molecule, so 2 electron is present only in the bonding molecular orbital. So it is represented as the electronic configuration for after the molecular formation. The electronic configuration is written as, we already said that the bonding molecular orbital is represented as sigma pi del. Here the sigma orbital is present, bonding sigma molecular orbital is present. So it is represented as sigma 1s, the 2 must be present in the superscript level. So the sigma 1s2, whereas in the sigma star 1s orbital, that is anti-bonding molecular orbital, there is no electron available. So only the 2 electrons undergo to the lower energy bonding molecular orbital. So then the bond order calculation, from the bond order calculation we calculate that the bond order is equal to 1, that is only the electron is present in the non-bonding molecular orbital, 2 electron, 2 minus 0, whereas no electron is available in the anti-bonding molecular orbital. So 2 minus 0 by 2 is equal to 1. So from this we conclude that between the 2 hydrogen atom in the hydrogen molecule, there is only one covalent bond is present. So in addition to that, the 2 electron is paired in the bonding molecular orbital. So it is a diamagnetic compound molecule. So from that we conclude that hydrogen molecule is a diamagnetic molecule. Next, the MO diagram for lithium molecule. The next atom is lithium. The lithium having the atomic number 3 and its atomic electronic configuration is 1s2, 2s2, 2p1. That we in the MO diagram we won't need to represent all the atomic orbital. That 1s orbital is already having the completely filled cell. So only we concentrate only in the outermost orbital 2s and 2p orbital. So we have to explain the MO diagram only for the 2s and 2p atomic orbital. So here we represent only the 2s and 2s orbital here. So the lithium having atomic number 3, so the electronic configuration is 1s2, 2s1. So we concentrate only in the 2s1 orbital. So we choose the 2s1 orbital, atomic orbital. So in the 2s1 orbital, one is present for one lithium atom is present in the left side, and another one 2s1 orbital is present in the another right side. So these having 2 unpaired electron which is present separately. When these 2 unpaired electron, that is 2 atomic orbital, 2s atomic orbital combine to form the 2 molecular orbital. One is bonding molecular orbital is represented as sigma 2s. In the previous hydrogen molecule we said that the formed molecular orbital is sigma 1s, because here the 1s atomic orbital is combined, whereas in the lithium we already said that 1s orbital is completely filled. So we won't need to discuss their MO in MO atomic orbital representation in the MO diagram. We have represent only the outermost orbital 2s1. So their representation is sigma 2s. So the bonding molecular orbital is sigma 2s and anti-bonding molecular orbital is sigma star 2s. When this 2 atom is present, when this 2 electron is present, their electron is going to the bonding molecular orbital sigma 2s2. It is represented as sigma 2s2, whereas the sigma 2s star is having no electrons. So their bond order is Nb minus Na by 2 is equal to 2 minus 0. So it is also having the bond order having 1. So from these we conclude that between 2 lithium atom there is only one covalent bond is present. This is a MO diagram for lithium molecule, that is Li2 molecule. Similarly, the MO diagram for B2 molecule, that is boron molecule. We know that the boron having an atomic number of 5. So their electronic configuration is 1s2, 2s2, 2p1. So, as usual we won't discuss the atomic orbital combination of 1s molecular orbital because it is completely filled. So, we concentrate only in the outermost orbital, that is the 2s and 2p atomic orbital. So, it is represented in the MO diagram for the boron molecule. First we show that 2s atomic orbital which is represented in the lower energy level, whereas the 2p orbital which is presented above that 2s atomic orbital present in the left side as well as the right side in the for 2 boron atoms. When the 2s atomic orbital of one boron atom is combined with another 2s atomic orbital of another boron atom to form the 2 atomic bonding molecular orbital. So, it is represented as sigma 2s and another one is sigma star 2s, and their electron filling is go to the, here it having 2 electron in the 2s and another 2 electron in the another 2s atomic orbital in boron atom. In the bonding molecular orbital totally we have a 4 electron in the atomic orbital. So, it is distributed based on the Afa principles. So, first the sigma 2s orbital is filled by 2 electron, the remaining 2 electron is go to the upper antibonding molecular orbital, that is sigma star 2s orbitals. So, this is a 2s orbital combination. Next we go to the 2p orbital. We already know that in the p orbital we having a 3 energy levels which is in the degenerate level, that is both the 3 orbital are in the same energy level, px, py, pz, but only one electron is present in the 2p orbital of each boron atoms. It is represented here. The 2p orbital of one boron atom is combined with another 2p orbital of another boron atom to form 2 type of orbital. One is sigma orbital and another one is pi orbital. Here the pi orbital having 2 energy level, whereas the sigma orbital having 1 energy level. So, in the boron molecule this pi energy level are in the lower energy level. So, the pi orbital is present in the lower energy compared to the sigma. So, first so having we only totally 1 electron is present in each boron atom. So, totally 2 boron atom. So, these 2 boron atom is distributed in the pi orbital. We already know that from the Pauli's exclusion principle, it is said that when the orbital having the 2 energy level or when the energy level having a 2 orbital are in the same energy, when the electron must be distributed only if it is unpaired. That is, the 2 electron must be distributed equally to the 2 orbitals. So, we are having pi 2px1 and pi 2py1. This is the distribution, electron distribution for the boron molecule. So, from the bond order calculation we conclude that only 2 electron is present in the boron molecule. So, their bond order is 1. So, this is the representation. Here the bond order is calculated only for the pi orbital distribution, pi bonding molecular orbital. Here the 2s bonding molecular orbital, already the electron is distributed. So, already the electron is completely filled. So, it is not need to calculate bond order for the 2s. So, only we calculate only the bond order for the 2p orbital. Otherwise, we can also calculate overall electron distributions for this 2 orbital. From this we conclude that they having the totally 4 electron is present in the bonding molecular orbital, whereas 2 electron is present in the anti-bonding molecular orbital. So, it is represented as 6 minus 4 by 2 which is equal to 2. So, the bond order is 1. This is the MO diagram for boron molecule, this is the MO diagram for carbon molecule, whereas the atomic number for carbon is 6, so having the electronic configuration 1s2, 2s2, 2p2. Similar to the boron molecule, there is one more electron is present in the 2p orbital. So, the boron having 2p2 configurations for each carbon atom, for each carbon atom it is represented in the MO diagram. We already know that how the 2s orbital is combined to form the molecular orbital. Then the 2p orbital of each carbon carrying 2 electron is combined to form the molecular orbital. The bonding molecular orbital is, first bonding molecular orbital is pi 2 px, pi 2 py, and another next higher energy bonding molecular orbital is sigma 2 pz. Then next higher energy anti-bonding molecular orbital is pi star 2 px, pi star 2 py, and the next higher energy anti-bonding molecular orbital is sigma star 2 pz. This is a pictorial representation for the MO diagram for carbon molecule, and this electron is distribution based on the half-half principle. First the sigma 2s orbital get the 2 electrons, and another sigma star 2s atomic molecular orbital get another 2 electron to form the 2s atomic orbital formation of molecular orbital. Then the 2p2 atomic orbital is combined. Here the 2 electron is present in each carbon atom. So totally 4 electron is present in the carbon molecule. This 4 electron is distributed as all in the pi atomic orbital, pi bonding molecular orbital, that is 4 electron is distributed equally in the pi 2px2 and pi 2py2, and the electronic configuration after the molecule formed is represented as sigma 2s2 to sigma star 2s2 to pi 2px2 pi 2py2, and it is represented here, and the bond order is here. The bond order for the 2p atomic orbital having 4 unpaired electron, so it is represented as 4 by 2, so it is equal to 2. So the bond order for carbon molecule is 2. From that we conclude that between 2 carbon atoms there is a 2 bond is present between the 2 carbon atom. In addition to that, this 4 electron is present in the pi bonding molecular orbital is completely filled, so it is diamagnetic character. Similarly, in the MO diagram for nitrogen molecule, there is a similarity between MO diagram for nitrogen, carbon, boron. Here all these molecules, the pi bonding molecular orbital is present in the lower energy level than sigma 2p bonding molecular orbital, whereas in boron pi bonding molecular orbital is lower energy level, whereas in carbon pi bonding molecular orbital is lower energy level than sigma 2p, whereas similarly in nitrogen also this pi bonding molecular orbital is present in the lower energy level. This is a similarity between the boron, carbon, nitrogen molecule MO diagram. Here in the nitrogen molecule there is the 3 unpaired electron is present, because the atomic number for nitrogen is 7, 1s2, 2s2, 2p3. So 3 electron is present in the 2p orbital. This 3 electron is distributed equally among the bonding molecular orbital formed. So first based on half-half principle, the pi 2px and pi 2p orbital accumulate 4 electron. The remaining 2 electron is go to the another higher energy level sigma bonding molecular orbital. So this 6 electron is distributed among these 3 bonding molecular orbital and is represented here. From the bond order calculation, it is concluded that totally 6 electron is present in the bonding molecular orbital, and so their bond order is 3. From that we conclude that between 2 nitrogen atom there is a 3 bond is present between this nitrogen molecule. This is a MO diagram for this is a MO diagram. Similarly, the oxygen molecule also shows the same MO diagram. Only one variation is oxygen having a 2p4 configuration. So, is having one more electron present in the 2p orbital for each atom. So, totally 2 electron is available for oxygen molecule. So, these 2 electron is go to the pi 2px, pi star 2px1 and pi star 2py1 for oxygen molecule. So, 2 unpaired electron is present in the anti-bonding molecular orbital, and their bond order for oxygen molecule is 2, and it is paramagnetic character. Nitrogen is having diamagnetic character, whereas oxygen having paramagnetic character. This is the last topic, heteronuclear diatomic molecule, that is both the atoms are having different atoms. Here we discuss the MO diagram for carbon monoxide molecule. We know that the carbon and oxygen, carbon having atomic number 6, oxygen having atomic number 8. So, from this we conclude that the carbon is having lower electronegativity than oxygen. So, the carbon atomic orbital having higher energy than the oxygen. Oxygen atomic orbital having lower energy than carbon. So, this is the electronic distribution, and from that we conclude that here the bond order is equivalent to 2. So, from that we conclude that between the carbon and the oxygen there is 2 bond is present between the carbon and oxygen, and the MO diagram is represented here to sigma 2s, sigma star 2s, pi 2 px, pi 2 py, sigma 2 pz, pi star to px, pi star to py, and is pictorially it is represented here. Thank you for watching this video. This video explained the MO theory, and it is also explained the magnetic properties, and is useful to you all. See you in the next class. Thank you.